Okay, so let's do another example. Now this one is called noncompetitive inhibition, and as you can see, we have inhibition chemical I. It's going to both the free enzyme and the enzyme substrate complex, and these will make even more enzyme substrate complexes. Like one of them is ESI and the other one is EI, and this is not necessarily the only kind of non-competitive inhibition that you'll see. This one we make a few assumptions, so we end up actually closing this loop. Like you'll see how we make these two extra complexes. We can close the loop by adding this, by assuming that these complexes react with each other with the same equilibrium constant Km. That might not necessarily be true for all kinds of non-competitive inhibition cases. We did this because it kind of simplifies the math a little bit, so that we can model the product formation rate a little bit more easily. So let's solve this, and let's find what the product formation rate is, and you'll see that again it's all the same as before. We can use the fast equilibrium assumption. Let's first start off with the product formation rate. And it's the same as before, very easy in this case, just K2 times the ES complex concentration. And for the fast equilibrium assumptions, forward rate equals the backwards rate. And we just solve in terms of the complex. And actually, yeah, we'll call this that equilibrium constant big Km. So don't mix up the little k with the big K's. And let's see, we can do it for the other ones. Now we have a lot of these complexes, but you just have to work through it slowly. And we do the same thing for ESI. And we simplify because ES can be like substituted in here. Okay, good. Now we'll use the enzyme conservation to create another equation. Now we have lots of these enzyme substrate and all of these complexes, but we just work through it. And you'll see the math checks out. And we substitute in those values. Remember, I'm skipping steps so you can work this out more thoroughly. I've gotten so used to doing this, I can skip steps. And all of the math just starts looking the same after you keep doing this practice. Okay. And remember that we substitute this back into ES because it's K2 ES, and ES is a function of E. We can substitute that in to remove E. Let's do that. And then the numerator has a Km now. And yeah, we just keep doing this. And then we'll have to try to see if we can get it into the Michaelis Menton form that we want so badly. Can we do it? Let's distribute the denominator. And we just work through it. Okay, what can we do? It is quite messy. We can factor the S's and the Km values. And it looks like if we want the Michaelis Menton form, we'll have to do that. Okay. And you'll see, oh look, it's this common 1 plus I over K that we keep seeing when we do inhibition. Okay, good. And you know, we can actually just, this whole thing is just a factor. So what we can do is just divide numerator and denominator by that factor. It's just constants. 1 plus I over Ki is a concentration, but in this case it's a constant. Ki is also a constant. So let's do this. See that? It's just multiplying by 1. And you'll see it actually cancels out nicely on the denominator. Wow. See how it looks so beautiful? And now we can get the Michaelis Menton form by letting the top piece. And again, these are just constants. Let that be the maximum velocity. Nice. But the thing is since it has that inhibition in it, we'll call it VM app, which is just a VM apparent VMAP, just to distinguish it from the cases where there's no inhibition. Now, let's look closely at this. See how we increase the denominator? In the case of no inhibition, I will just be 0, and then you just end up getting what we got before for the no inhibition case. How does this compare, this VM map? Whoops. How does it compare to VM? Remember before, VM was just K2E0, and you can see here we're increasing the denominator, so it's clear that VM applied is lower than VM, and if the maximum velocity VM, it has a very strong impact on your product formation rate. And you can tell here that if you end up doing this, if it has this kind of inhibition where you're increasing the denominator, you're going to be decreasing VM applied, and you know, it's going to be clear that the product formation rate of P is going to decrease in this case. There's no doubt about it. And yeah, that's how you can model the product formation rate for non-competitive inhibition. It's not too bad. Again, it's just the same old stuff. Just work through it slowly. You don't have to do it as fast as I did. Just make sure you don't make any mistakes. And that's how you do the kinetics for this kind of problem. Hope you enjoyed the video.